So let's add a few more details about the reconstructed climates and a little bit more details about the isotopes as well. Here is a nice paper that just came out literally a few weeks ago, I think, 2101 maybe, 2021. When we reconstruct past climates, there are often details that are not complete, and people keep adding more information to the reconstructions. So here is the reconstruction of the paleo temperature over the Holocene. There has always been an issue about what the so-called Holocene optimum temperature, I don't know if I want to go, so we had mentioned something like climatic optimum here. So we know much more about medieval warming, during which the Vikings occupied Greenland and went all the way to North America, and then they got pushed out of Greenland or went extinct because the medieval warming ended and Greenland began to freeze again, and the Little Ice Age came along, which extended the freezing deep into Europe and so on. So all these kinds of things that combine various types of evidences leave some debates open. So a recent work has reconstructed things to say that when you look at seasonal temperatures, so when you reconstruct past evidences, you have to be sure about the sampling of the proxy you are using and whether it is capturing the seasonal changes or the annual mean changes. For example, if summers are getting warmer in a record but it doesn't say anything about what happened in the winter, you might end up biasing the reconstruction, which is kind of something that kind of the thing that happened in the past reconstructions. So this one talks about further details. So it looks at combined records of atmospheric CO2 here, which was at 280 ppm coming out of the last ice age. We will see later on that the ice age to glacial to deglacial times, the CO2 in the atmosphere varies by about 80 to 100 ppm. So it remained the same for a while and then started increasing. A combination of human activity, deforestation for agriculture, population growth, and so on. Bill Ruddiman writes more about how Holocene CO2 already shows human impacts and so on. And then came the Industrial Revolution, where we shot up beyond anything we have seen for a long time. So receding ice and recovery of the temperature was dominating this period here, where the seasonal temperatures increase and the mean annual temperatures increase, but not as much. And then the greenhouse gases increased, maybe also methane from cattle and agriculture and wetlands and so on. So seasonal temperatures here showed a different behavior than mean annual temperatures. So the long story short, one has to reconstruct. So remnant glacial ice kept global temperatures cooler over here. So ice age ended, but lots of mountain glaciers in the Alps, Himalayas, high latitudes, Greenland, etc. were still in the ice age mode, slowly melting away. So that effect was overwhelmed by the rising greenhouse gases, which then affected the seasonal temperatures and the annual temperatures as well. So here today, global mean temperature was colder here, warmer here, Industrial Revolution. Today we are 2.5 degrees C warmer compared to the end of the ice age. CO2 is 160 ppm higher than 12,000 years ago. So these are also very critical. In terms of isotopes, I should say more. We said that there are isotopes which are radioactive and have a half-life over which they decay into a daughter isotope. The parent isotope decays into a daughter isotope. But there is also other ways that isotopes are used. Life in general fractionates. So these are stable isotopes sometimes. For example, oxygen, which we know as O16, tends to have isotopes of O17 and O18. So a particular element is obviously defined by its atomic number of protons, and number of neutrons can change. So if, as long as it has 8 protons and in its core, it remains oxygen, and when you add a neutron, which is always possible, as we will see with C14 for example, then you can have an oxygen that has got a different mass number. So here you have 8 protons and 10 neutrons, so you have O18 and you also have an O16. And how do we use it? Basically O18 is heavier than O16, and when evaporation happens, for obviously energy reasons, atmosphere will pick up more O16 than O18, so H2O in the atmosphere will have more H2O16 than H2O18 on average. So that means ocean can have more H2O18 compared to the atmosphere. So whenever you go in the past and take a ice core sample or any other sample where you have some kind of oxygen signature buried, you can use these ratio of O18 to O16 and compare it to some standard that we expect for a given climate, and then you can compare this kind of delta. So then the deficit or the surplus compared to a standard is referred to as delta O18. And this can be related to temperature, because if you have warm temperatures there is more evaporation. If you have cold temperatures and more glaciers are forming, then you are taking out O18 at a certain rate and depositing into the ice at a certain rate, right? So depending on where you look, you can get a difference in the O18 of the past proxy compared to the standard, and you can interpret that in terms of temperature, for example. Okay, so if it is not clear, look at here. Okay, so we're looking at a scale here, approximately lower delta O18. So this is the delta O18 formulation, but just think of more O18, and higher O18, lower O18. So ocean has a certain delta O18. When evaporation happens, the atmosphere has a lower O18 than the ocean. You can see the scale here, because evaporation picks up the lighter isotope, which is O16, so it is deficit in O18, so delta O18 is lower. As it moves typically with the circulation towards higher latitudes, there is rain along the way, right? So the rain preferentially drops more O18 because it's heavier. So now you have even further reduced the O18 in the clouds compared to here, and you have taken some of that O18 and put it into the groundwater here. Okay, so then along the way you are having exchanges between various levels of O18 directly by evaporation or through transpiration, evapotranspiration, and so on. And as you go to higher and higher altitudes or latitudes, you can begin to create different delta O18 values. So that's how you end up with proxies that can tell you what the temperature is. So if the glacier is building, let's say a mountain glacier is building, then you can see that this has been completely depleted of O18 by now, because along the way by various processes it has lost the O18, and it is dropping the O18 into the snow, and the cloud has very little O18, and more of the O18 is getting into the soil. So The more you evaporate, the heavier the O18 in the ocean is going, or the higher the delta O18 in the ocean going to be, because O16 is relatively being removed, so the ratio is what matters. And the more you begin to take it and dump it here, the more O16 is going to be locked up here, because the deficit in O18 is higher and higher as you go forward. So just stare at this figure for a little bit. It sounds complicated, but actually it's fairly straightforward. And this information can be used also to look at O18 signatures in animal teeth and bones, for example. Animals are inhaling O2. There is a food component of the structural and oxygen and food water oxygen coming in, and they're also drinking water. The body is processing it, taking up nutrients and locking up into bones. Why bones? Because they get preserved for a long time, right? So they're ejecting water vapor and water in the waste, and they're respiring CO2. So then these evidences can also be used to look at their diet, their past climate, and so on and so forth. Okay, so O18 is a very good example. Another good example is a carbon. So carbon fractionation also happens because carbon has stable isotopes of C12 and C13. It also has an unstable or radioactive isotope of C14, which is used for some nice climate reconstructions as well. It's also a good paleo proxy. Okay, so I hope it's clear. Again, it sounds complicated, but listen to the podcast again if you want, and make sure you understand it. The concept is beautiful, the chemistry is beautiful, and its usefulness is just amazing. So you should make sure that you understand it. Okay.